So in this day of notes, we're going to take a look at a few more examples of geometric type word problems. We've already gone through a variety of different um, ideas and thoughts of how to use word problems. And so today we're going to take a look, go back and redo some of them just for more practice. So example number 1 says a rectangular enclosure will be built off of an existing wall, so there will only need to be 3 sides of fencing. What is the maximum area you can enclose if you only have 80 feet of fencing? So the first thing that we have to do is we have to start by making a picture of the situation. So we have an existing wall. This does not require us to use any fencing to create this. This already exists. And what we're going to do is we're going to build fencing off of three sides of fencing to enclose a rectangle. So I do not know what the length of this is, and I do not know what the width of this is. I'm going to call the length of this x. And remember that a rectangle has opposite sides equal. So if this left-hand side is x, then the right-hand side is x. This other side right here, I don't know its length, but it doesn't have to be the same as x, so I'm going to call it a different letter. I'm going to call it y. One of the things that we know about this problem is that the area of this rectangle would be length times width, so x times y. The trouble is I can't solve a problem that has two letters in it. So x times y, I wouldn't even be able to plug it in my graphing calculator. However, the second thing that I know in this problem is that I have a total of 80 feet of fencing, which is my perimeter. So if I take the two pieces that are labeled with x and the one piece that's labeled with y and add that up, that should add up to make the 80 feet of fencing that I have at my disposal. And if we take this equation and rearrange it to solve for y by moving the two x's over to the other side, you would get that y has to equal 80 minus 2x. Now that we have solved that equation for y, we can replace, or the more mathematical word for this is substitute. We can substitute the 80 minus 2x into the formula where the y goes for area. So our area formula now becomes x times parentheses 80 minus 2x. This area formula I can solve and work with and graph because it's now down to just one kind of letter. But before I go typing this into my graphing calculator, I am going to need to figure out what is the domain for this problem. What are the possible values for x? And first of all, because x is the width of the rectangle, we know that the lowest we can go is 0. And because two of the pieces in the picture are labeled with x and we only have 80 feet of fencing, even if I decided to use all of my fencing to make those two pieces that are labeled x, that means the biggest I could go for x would be 40. So for my graphing calculator, this is going to be my x min, and this is going to be my x max. And then I could do zoom fit to get my graphing calculator to figure out what this graph ought to look like. So I actually have my graphing calculator all ready to go. So let's pull it up. And the formula that we're going to be graphing is x times parentheses 80 minus 2x. And before I just hit the graph button, because if I hit the graph button right now, I'm not going to see much of anything. I want to go to the window button and I want to put in what my smallest x value is going to be, which is 0, and what my biggest x value should be, which is 40. And then I'm going to hit zoom and pick option 0, which is zoom fit, and it will fit this graph within my viewing window perfectly. So I know my x-axis goes from 0 to 40, but let's find out what my y-axis scale is. If I hit the window button, I can see that the y-axis goes up to 800. So let's make a graph of this on our paper. So I'm trying to make what I just saw in my graphing calculator. We have an upside down parabola that goes from 0 to 40 in the x direction, and it goes from 0 to 800 in the y direction. We want to put the equation on here. So the area was equal to x times 80 minus 2x. And this problem is asking you to find the maximum area. So basically we want to find the peak of that graph. So if we go back to our graphing calculator, and there's the graph. If we hit second trace, option number 4 is going to be to find a maximum. We want to put our cursor to the left of where we think the maximum is, hit enter. Put our cursor to the right of where we think the maximum is, and hit enter. And then there's only one peak in between there, so we can hit enter. And it turns out your maximum area, which is the y coordinate, because remember the y equation is set equal to the area, y is equal to 800, that is going to be your maximum area. So to answer the question, the max area that you can enclose is going to be 800 square feet. And that happens right here. When x was 20, my y value was 800. Okay, so there's our first problem. In the second problem for this day's notes, we're saying that a box with no lid will be formed from a rectangular piece of cardboard by cutting rectangles that are twice as long as they are wide from each one of the corners. Top and bottom flaps will be folded once, and the left and right flaps will be folded twice to increase the strength of the box. If the original piece of cardboard is 50 inches by 22 inches, what width cut makes the volume turn out to be exactly 1,500 cubic inches? All right, so let's start off with a drawing. This is the original piece of cardboard. They told me it was 22 inches wide by 50 inches long. Okay, so this time, instead of cutting squares out of the corners, we're going to be cutting rectangles that are twice as long as they are wide. I don't know what the width is. I'm going to call that x. And if it's twice as long as it is wide, then the width is going to be 2x. And I'm going to do that in all four of my corners. 2x, x. 2x, x, 2x, and x. Okay, so basically what I'm going to do here, I'm going to use my eraser, and I'm going to erase out these corners because those are the pieces that are being cut out. Okay, so this is what we have left. The top and the bottom flaps are going to be folded once. So I'm going to fold along these dotted lines. So the top part will simply get folded up and the bottom part will simply get folded up. For the left and the right flaps, we're going to fold them twice. First, I'm going to fold it in half, and then I will fold it up. Same thing on this side. Fold it in half once, and then fold it up. So this is the picture. The dotted lines are where the folds are going to happen. So the next thing that we need to do is, this problem really wants to talk about volume. So we're going to have to figure out the volume of the box after all of the cutting and after all of the folding is done. Well, the new length of my box is only going to go from here to here. And the formula for the volume of a box in general is length times width times height. So we have to figure out what those new lengths and widths and heights are. Well, I started out with a length of 50 inches, but I'm cutting two x's from both the left and the right-hand side. So my new length is going to be 50 minus 4 x's, 2 off of each side. My new width is not going to be 22 inches anymore. It's going to be 22 minus 1 x off the top and 1 x off the bottom. So that's going to be 22 minus 2x. And after all the cutting and after all the folding is done, remember that the left and right sides are getting folded in half once and then folded up. The height of my box on any of the sides would end up just being x. So this is my formula for the volume of the box. Again, one of the things that we ought to do before we go typing this into our graphing calculator, we have the correct formula, but let's take a moment to think about what our domain is going to be. Again, x represents the width of a rectangle. The smallest that can be is 0. And the biggest it can be, we have to prevent from cutting more than halfway across our box. So we cannot let x go more than halfway across in either direction. So your maximum value of x is going to be 11, because if you went bigger than 11, you'd be going more than halfway across the box, not leaving anything left for the flaps to fold up, since it's only 22 inches wide. So what we now want to do is we want to use our graphing calculator to make a graph of what this volume looks like. They actually have a very specific volume in mind. They have a volume of 1,500 cubic inches in mind. So one of the things that we're going to want to do when we go to graph this is we're going to want to have our graphing calculator draw us a horizontal line at 1,500 cubic inches. And we would also want to graph the equation of the volume to see where they actually intersect with each other. So this is going to be x. This is going to be volume. And let's take a moment right now to actually get this up on the graphing calculator. So if I go to my y equals screen, the first thing I have to do is clear out what was in there. and the length was 50 minus 4x, parentheses, and then we have a width of 22 minus 2x, and a height of x. There's my volume formula. And on line number 2, y2, I'm going to have it draw that horizontal line at 1500 cubic inches. Now again, I'm going to have to adjust my viewing window. We've already said that x min should be 0, x max in this problem should be 11. We know that y min is going to be 0, and we know that the y max has to go over 1500 cubic inches. So I'm going to let it go all the way up to 2000 just to see what that looks like. And there's my graph. So this is a pretty good graph. In fact, I wouldn't even mess with this viewing window anymore. I can see the places where the volume curve and the 1500 cubic inches line cross. And so that's going to be my next step, is to find those points of intersection. So, but first, let me try to graph what we've got so far. So we have a graph here that goes from 0 to 11 in the x direction. It goes up fast and it comes down slow, and it crosses through the 1500 cubic inch line. Make sure that you put your formula that created it on the graph. So 50 minus 4x times 22 minus 2x times x. And the rest of the graph is labeled. We got labels for the x-axis, y-axis. We might want to say the fact that this goes all the way up to 2000. Okay. So now the last thing that we have to do is use our graphing calculator to figure out where those points of intersection are. So we're going to hit second trace, option number 5, to find a point of intersection. What do you want to be your first curve? What do you want to be your second curve? What do you want for initial guess? Now, where my initial guess is right now, it's actually going to find the answer to the right first, and that happens to be 6.1996889. So let's round that off to 6.20. And then if we go back and redo that again, second trace, option number 5, to find a point of intersection. What do you want to be your first curve? What do you want to be your second curve? This time for an initial guess, I'm going to use the left arrow, and I got to get my initial guess way further over to the left so I can find the other answer, which is apparently at 1.97. Round it off. Okay, so the answer to this question is the two different x values that would cause my volume to turn out to be exactly 1500 cubic inches were 1.97 and 6.20. So x equals 1.97 or 6.20. That is, let me just go back, what is the width of the cut? And if you look at your picture, the width of the cut is x, so we have properly found the answer for this question. So the last question that we have is kind of similar to one that we had done before in the notes. A soup manufacturer knows that the volume of soup that it needs to put into a cylindrical can should be exactly 5 pi cubic inches. Determine the radius and height of the can that minimizes the total surface area of the can. And again, I'm giving you the formula for the volume of a can and the total surface area of the can with that picture over there for the radius and the height of the cylindrical can. Okay, well, first of all, we have two equations that both involve the letter H and R. We cannot solve a problem that has two variables in it. I do know that the volume was supposed to turn out to be 5 pi cubic inches. So I'm going to take my volume formula and set it equal to 5 pi. That means that the pi on the left-hand and right-hand side of this formula cancel out. So we have 5 equals r squared h. And if you want to solve that for h, you could simply just divide both sides by r squared. So h is equal to 5 divided by r squared. Now the reason that I'm doing this is because we're going to use a process called substitution, whereby now that I know what h is equivalent to, it's equivalent to 5 over r squared, I can use that and replace it into my other formula. So now for my total surface area, I know it's going to be 2 pi r squared, so the total surface area equals 2 pi r squared plus 2 times pi times r times my height, which I'm replacing with 5 over r squared. And again, there's going to be some cancellation here. One of these r's cancels with one of these r's. So my total surface area formula is going to be 2 pi r squared plus 2 times pi times 5 divided by r. Or in other words, that's going to be 10 pi over r. Let me make that replacement. So 2 times pi times 5 is 10 pi over r. Okay, so this is the formula that I'm going to want to put in my graphing calculator. And what we're looking for here is a minimum, because we're trying to minimize the surface area. The reason why this is going to work is because this equation now only has one type of letter. So let me type that into my graphing calculator. So I'll clear out what I had before. Clear, clear, go back up. We have 2 times pi times x squared plus 10 pi divided by x. Okay, again, if I graph this in my standard viewing window, probably not going to see too much of anything. So we have to realize that x, which is your radius, has a minimum value of 0. And I'm just going to leave 10 as the maximum value for now. For y min, I know that my surface area cannot be negative, so we're going to go down to 0. And for my y max, I don't know, I'm going to try like 200, I guess. I don't know. We'll give that a shot and see what it looks like. There we go. So our graph comes down, turns around, and goes back up, which is very good because we're looking for a minimum. And I'm pretty sure I'm going to be able to find that minimum on my graph. First, let me make this graph. So remember, if we're going to get a solution graphically, we need to make the picture of the graph. So we had a graph that went from 0 to 10 in the x direction, where x is our radius. And this y-axis represented our total surface area. It looks like it comes down and then goes back up somewhere in here. So if we go back to the picture on our graphing calculator, what we're going to try to do here is we're going to try to find the minimum. So second trace, option number 3. For a minimum, they're going to want you to have a left bound. So that means I have to move the cursor to the left of where I think the answer is. So maybe somewhere like here. And then a right bound. So I have to go to the right of where I think the minimum is and hit enter. And then what do we want for initial guess? So it turns out that the x value that is a minimum for this is about x equals 1.3, I'm going to round that off, 1.36. So that would be my radius that produces a minimum surface area. So this spot right here is at an x value of 1.36. So your radius that produces the minimum surface area is 1.36. But I have not fully answered the question because they wanted both the radius and the height that produces the minimum surface area. I have the r. Now I have to figure out what the h is. We have a formula right here for h that is 5 divided by your radius squared. So if I take that 1.36 and square it and divide it into 5, so 5 divided by 1.36 squared is going to give us a height of about 2.70. Both of these, by the way, are going to be in inches. Those are the units, because I know it's in inches because the volume was in inches cubed. Okay, well, that's the end of today's lesson. You are now ready to try the homework for tonight.